Right, so with this question here, you can see that before the collision, they're going towards each other, as it says there, right? So A with speed 5, B with speed 3. So you can see the speeds going towards each other there because that's the direction of motion of both of them. After then it says A has reversed its direction after the collision. So you can see I've got A going backwards with a speed of 2, okay, going this way. So the arrow's pointing that way. And then part A, then they're asking us to work out what the speed of B is. Okay, they're asking us to show this 2.25. So I'm going to assume that B gets reversed as well. I'm just assuming it's going that way, might not be. So let's just assume we've got that direction, and we'll see what we get. So we're going to take this direction as positive, of course, with momentum. And then whatever VB comes out to be, we'll be able to tell what direction it's going in. But they want the speed, so it should come out 2.25. Now, of course, conservation of momentum, okay, we use, and that means the total momentum before of the system is equal to the total momentum after of the whole system. It's important to recognize that we're not just focusing on one particle, okay, in terms of looking at the momentum. We're looking at the total momentum of the whole system combined. These two objects will equal the total momentum combined of these two objects afterwards. So momentum, of course, is mass times velocity. So we 3 times 5 in this case. Add then the momentum of this one. That'll be 4 times the velocity of this. But remember, because it's going backwards, we'll do 4 for the mass times velocity there. Going backwards means it's minus 3. Okay, the arrow shows it's going in the reverse direction, okay, towards A, and it's opposite our positive direction. So you've got to put minus 3 there. You've got to take note of the direction. We've got velocities, so it's going opposite to our positive direction. Now afterwards then, of course, we've got momentum of A, which will be 3 times velocity afterwards, which will be minus 2, yeah, because we told the direction gets reversed of A. And then we've got this then, plus 4 then times the velocity of B. So a bit of calculated work there maybe, and we end up with 3 there, minus 6 there, plus 4B. Take that over, so you get 9 equals 4 VB, and then that implies then that VB is 2.25 meters per second, exactly as they wanted. It's positive, so actually I got the direction right, okay, but they asked for the speed, and that's exactly what it is, and it is going that way. Part B then says find the coefficient of restitution between A and B. Okay, so remember, with the coefficient of restitution, okay, it's given this value E, okay, you just got to remember that. When you see those words, coefficient of restitution, it's the value E, and basically it's the speed of separation divided by the speed of approach. Okay, that's the way I like to remember it, but the other formula for it, okay, the formal formula for it is basically VB minus VA, okay, which is talking about the velocities after, isn't it, after the separation. Okay, separation obviously occurs after the collision. Speed of approach then will be UA minus UB, so you could use that formula as well. And there's a bit of a ring to it, isn't it, because VB take away VA, and then UA take away UB. So it's sort of symmetrical in a sense. You start with B, end with B, and then you've got the A's in the middle when you read that out. But essentially, you could just think about the speed of separation. Now, of course, this was equal to 2.25, wasn't it? Yeah. So if this is going back to, that's going forward 2.25. Think about how that's separating. Of course, overall, the separation speed there is going to be 4.25, isn't it? Because that's going one way, 2.25, that's going the other way, 2. They're speeding away from each other, so you're going to add those totals, okay, to see how the speed is separating. So 2.25, you're going to use the formula, you'd have your VB to be 2.25, which is that one there, but then you take away your VA, and remember VA would be minus 2, because it's going backwards. So you can see where I get 4.25 from. Over then, now speed of approach, so you can see this is going 5, that's going 3, but they're going towards each other, so we can have a mega crash. So the combined speed is actually 8, isn't it? Yeah, when they crash into each other, because one's going 5 but the other one's going 3 in reverse, so it's combined of 8. But if you use this UA, which is 5, take away then UB, which is that one there, which of course is -3. It's going in the opposite direction to positive. So let's work that out. We get out 0.53125. Okay, there's my answer there. Okay, or you could write as a fraction 17/32. Okay, and then just to finish it off, it says determine the magnitude of the impulse exerted by A on B. So on B, okay, so what's happening to B basically? That's what we're interested in. What impulse has been had on B, okay, with the effect of A crashing into it? Well, to work out the impulse on B, we need to look at the change in momentum of B. Okay, that's how you work out the impulse, to see how the momentum of B itself has changed. So that would be the momentum after, which is like mv, take away the momentum before, which is mu. And of course we're talking about object B here, aren't we? Okay, that's how you work out the change of momentum, just by taking them away to see what the momentum was after, take away the momentum before. And that will be a measure of the impulse. So the mass of B, of course, is 4. So the velocity after then is 2.25 in the positive direction. Take away then the mass, which is 4, and then the velocity before, of course, is 3, but it's going that way, so it would be -3. So then you can just work that out on your calculator, and we're done. So we get 21, and the units are Newton seconds.